In the previous lesson, we learned what are conversion factors, okay? And we also learned how to use this stoichiometry flowchart. Again, the word is stoichiometry. So stoichiometry. That's the word right there. Stoichiometry flowchart. This is a stoichiometry flowchart. And how we can use the stoichiometry flowchart using our given where we start and the unknown where we're gonna end, so that we take our given time the arrows to get to our unknown. Now we are going to learn how to apply this flowchart that we get from our stoichiometry flowchart to plug into the calculator so that we can actually solve out the whole entire problem. But before that, we need to realize this. What is conversion factor? So one of the most important things you need to realize is conversion factor is just basically a ratios of two different measurements that are equal in terms of values. For example, we have 100 penny relative to $1, and that can be expressed in terms of $1, isn't it? So that is a very basic conversion factor. Now, because a conversion factor can be expressed as a ratios, and when you think of ratio, you know it is a fraction. So how can I put this as a fraction? So you can think of this fraction is almost equivalent to the equal sign. So how does that work? Well, first of all, a fraction has a number on the bottom and a number on top. So what we have in this case is just one measurement on top and one measurement on the bottom. So let's put 100 penny on top. It doesn't matter, okay? 100 penny on top. If this measurement's on top, the other side must be on the bottom because there are only two places to be, either top or bottom. So we have $1 on the bottom. Now remember, a conversion factor is equivalence. That means they are equal in terms of values. If they are equal in terms of values, that means if I were to say that this equal to 1 and this equal to 1, don't they cancel out equal to 1? So because they are equal in terms of values, this can be simplified as 1. Why is that important? Because now you can actually rewrite this conversion factor or this fraction so that the dollars on top, $1 on top, and the penny is on the bottom. And they are equivalent or they are equal to each other. So it doesn't matter how you write it. They are the same values. So why is that important? Because in chemistry, you can actually change the grams all the way to liter. And I'm going to show you next. Let's look at an example, okay? So here is a problem that we've done so far in terms of setting up the flowchart. But the rest is that we had to plug this in a way that look like this fraction so that we can solve for the unknown. And notice in this problem, let's go back to this problem, let's read this problem together. At standard temperature and pressure, 1.3 grams of methane gas will have how many molecules of methane gas? So methane is CH4. The molar mass, notice how we have new term here, molar mass of methane is equal to 1 moles of CH4 equals to 6.04 grams of CH4. And doesn't that sound very familiar? That is because this is your molar mass right there. So as you can see, the nickname for this conversion factors right here is known as the molar mass. So when you are given the molar mass, think of this conversion factor. And if you look at this size of conversion factor, look at it very carefully. Notice how this conversion factor, do you see that they all have a numbers in front of each the measurement? Here we have 22.4, this one has 1 mole. Here we have 6.02 times 10 to the 23rd, and here we have 1. Except for this one where we have 1 mole, but we have this generic number signs. That is because we have to look for it. But I want to show you how to look for it later. For now, it is going to be given to you in terms of what? It is going to be called molar mass, okay? So molar mass is this number right there. So let's go back to our problem. So I have made the assumption that you know how to set this up already. So what we're going to do is start plugging in the number that is not there. Well, we know that the only time that the number's not there is when we go through that conversion factor. So this number right there, what is that number supposed to be? It is the molar mass. Okay, see the molar mass right there? It is the molar mass, which represent that number. So the molar mass is equal to what? 1 moles of A, which is CH4, equal to the number of gram of CH4, and that number is 16.04. So this right here is 16.04. So now all the numbers are on the flowchart. So how do we apply to this right here? Well, first of all, we're not going to do anything to this side. This is just telling that we are looking for molecule. So once we do the cross out of unit and chemical, your answer must be a molecule. So what do I mean by that? Well, starting from our given measurement, which is 1.3 grams of CH4, right? And it is time. Notice again, we can rewrite this as a fraction. We can rewrite this as a fraction. Now the question is this, which size or which measurement of the conversion factor will be on the bottom? In your math class, right, the basic math of all math is that if you have x over x, what happened to it? It cancels out, right? Now, why is that? Because they are the same, so it actually simplify into 1. Or if you have x times 1 over x, and what would that do? This x still cancel each other out, which is simplifying equal to 1. So we are going to do the same thing to our measurement and unit. In this case, we have 1 moles of CH4 equal to the number gram of CH4, specifically 16.04 gram. So notice how we have the unit gram of CH4 here, and we want to cancel that out so we can get all the way to molecules, okay? So if that is gram, we need to cancel it, so we must bring the gram on the bottom. So this side must be on the bottom. Now, does it have to be that side all the time? No. We are looking at the unit, because this is the unit grams of CH4. So therefore, we have to put grams of CH4 on the bottom. Specifically, how many? 16.04 CH4 gram. Again, we are looking at the unit. Left and right does not matter. Because this side is on the bottom, the other side of the fraction must be, well, the other side of the conversion factor must be on the top of the fraction. So we have 1 mole of CH4. And notice how gram and CH4 and gram and CH4 cancel out. Just like x cancel out with x. Isn't that easy? Okay. Now we move on to the next conversion factor. That's it. Let's move on to the next conversion factor. We are going to do the same thing. Well, in this case, here we have mole. Notice how we canceled grams already. Now we have the new unit mole of CH4. So we had to cancel moles of CH4. And if we look at this conversion factor, we have 1 mole of CH4 equal to 6.02 times 10^23 molecule of CH4. So which size of the conversion factor will be on the bottom? Of course, it has to be the same as this one to cancel out. Remember the structure, right? X cancel with X. So in this case, we have 1 mole of CH4 on the bottom. If this is on the bottom, okay, the other part must be on top. There is nowhere else to go because a fraction only have 2 places, either top or bottom. So we have 6.02 times 10^23 molecules of CH4. And then we are done. Isn't that? Look at this. Mole cancel out with moles of CH4. Just like we have X cancel out with X, or in that case, okay? And then what do we have in the end? The rest is just, when you combine them together, you basically multiply all the number on top, divide all the number on the bottom. Except, of course, when we have 1, we don't really care about 1. Because any number multiplied by 1 or is equal to itself, right? Or divide by 1 equal to itself. So we have 1.3 on top, right? This got cancelled already, and that got cancelled already, and that got cancelled already, and we can ignore the 1, time 6.02 times 10 to the 23rd molecules of CH4. And that's all the number we have on top. Pretty much it. Divided by, what's the next name list? Everything on the bottom. Sorry about the ugly line, but this is a fractional line, okay? What are the numbers on the bottom? Here it doesn't have any number on the bottom, so we move on to the next one. So we have 16.04, okay? And this is the 1, so we can ignore it. So this is our answer overall. And of course we can simplify this with a calculator. Let's plug this in our calculator so we can get our final answer. Isn't that great? We have 1.3 times 6.02, and remember this is represented by the button right here, the double E button, right? Or EXP, which is right here. Okay, so I press EXP, and what's the number right there? 23. Then I just continue. So this line represents division, divided by 16.02, or in this case 0.4, and then we have our answer. Isn't that great? This is our answer here, equal to 4.879, and we're going to keep how many sig fig in this case? So 2 sig fig, 3 sig fig, but for now let's ignore sig fig. How about that? Let's ignore sig fig. So we'll just focus around our answer so that we can have 2 decimal places. 4.88, because of that 9 will make it 7, times 10 to the 22nd molecules of CH4, and that is our final answer if we plug into the calculator. And that is a very big number, okay? Consider that we only have a tiny small number of grams of CH4, but that's how many molecules we have, and that 1.3 grams of CH4. Isn't that amazing? Now let's try another example. Again, I have everything set up for you already. We have carbon monoxide is toxic, colorless, odorless, tasteless gas that is slightly less dense than air. Okay, what does mean? We breathe in. At standard temperature and pressure, 1.3 liters of carbon monoxide gas will have how many grams of carbon monoxide? So how many gram can this 1.3 liter have? And the molar mass of carbon monoxide is 1 mole of carbon monoxide equal to 28.01 gram of carbon monoxide. So I have the flowchart laid out for you already. Okay, isn't that nice? Now let's go back to some extent how to cancel out. Again, we don't do anything with this, so let's save this along the line. So we can rewrite starting from a given. Okay, we have 1.3 liter of carbon monoxide and time. So going back to the ideas of this need to be canceled out so we can get our grams as we did up here, right? Notice how our final answer or final unit is molecule, and look what we're looking for, molecule CH4, molecule CH4 right there. Isn't that great? So our answers in this case, we have grams of CO as well. Now let's go back to this conversion factor. Again, rewrite as a fraction. If this is liter of CO, which size of the measurement will be on the bottom? If this is liter, we are going to put the liter on the bottom. So right here. So it's 22.4 liter of CO. Well, not CO2, but CO, okay? And then, if this side is on the bottom, the other side must be on top. So we have 1 mole of CO. Notice how liter of CO cancel each other out. Now let's go on to the next conversion factor. Look at the next conversion factor. We have 1 moles of CO equal to the number of grams of CO. Whoa, we don't have a number here, a specific number, because we cannot plug this generic number sign into a calculator. It wouldn't work. But, again, going back to our flowchart, look at that conversion factor. That is the molar mass, isn't it? See, look right there? The molar mass. Are we given the molar mass? Let's read the problem again. Oh, there you go. The molar mass of CO is 1 mole of CO equal to 28.01 grams of CO. So this number right here, it's actually 28.01. Okay, now we have all the number. Let's continue. So if this is mole, okay, this down here needs to be mole as well. So of course, this size will be on the bottom. So we have 1 mole of CO on the bottom. If this side is on the bottom, the other side must be on top. So 28.01 grams of CO. And notice how moles of CO or carbon monoxide cancel out and give us our unit grams of CO, which is exactly that one. Now let's rewrite this in terms of everything on top multiply together, divide everything on the bottom. Ignore the ones, of course. So we have 1.3 times 1. We can ignore that. Times 28.01 grams of CO. And then divide everything on the bottom, which is 22.4, times 1, which we can ignore. So 22.4. And there we go. We have our final answer. Isn't that nice? And if we want to plug this into a calculator, let's plug this into a calculator. It's not that bad. 1.3 times 28.01, okay, divided by, so you know I did it continuously, right? Do everything on top, then divide everything on bottom. Divided by 22.4. Voila. So we have what? We have 6.63 grams of CO. So if we have 1.3 liters of, in this case, carbon monoxide, within that 1.3 liter, there will be 1.63 grams of carbon monoxide. And that is our answer. Isn't that nice?